Okay, yeah, now we're starting our first session, and I'm happy to introduce the first keynote speaker, Mrinmaya Sachan. He is an assistant professor at ETH Zurich, where he works on natural language processing and connecting machine learning with education. And previously, he received his PhD from CMU, and got many awards, for instance, an Outstanding Paper Award at ACL 2015. So today he's going to talk about more literate AI and AI-powered learning technologies. Take it away.
Okay, hello everyone. Thanks a lot, Sean, for inviting me. Thanks a lot to the organizers for putting together this wonderful event. I'm excited to be here. And this talk is, as you heard, might seem a little bit different from what you heard from CN, but I promise you there are a lot of deep connections, for example, with human cognition and human learning, and maybe you can get to some of them. So let's get started. So over the last few years, we have witnessed this tremendous progress in AI, right, with these large language models. And these models have now entered our public conscience. And we keep on hearing from the press how ChatGPT has kind of kicked off an AI arms race, how GPT has now learned to code or blog or argue, how AI is now mastering language, but maybe we should not trust it entirely, how Google engineers are now claiming that their AI is actually sentient, right? So there are a lot of claims about these large language models, and they are truly exciting, and they're everywhere. But one of the things that is really exciting about these models, to me, is that they have really emerged as these general purpose problem solvers that are really exciting. And these models have shown a lot of promise in solving some of the very challenging educational problems that demand deep reading comprehension, deep reasoning, and integration of a lot of domain knowledge that was, until very recently, really thought of as like a domain of human reading and human competence, right? So here is this plot from the GPT-4 paper that some of you may have seen. A very basic summary of results. As you can see here, that on 16 out of the 26 standardized tests that were in their evaluation, the GPT-4 model does well than the 80 percentile test taker, right? So this includes a wide range of these test types. For example, this includes the Uniform Bar Exam, AP Statistics, AP Macroeconomics, SAT Math, the US government, art history, environmental sciences, so on, right? So these models are able to really do well on some of these very challenging problems. Now, there are also some controversies around this result, whether these models are really memorizing all of this information from the training data, but even if they are doing that, it's still impressive that we have something that has this kind of capability today. And this has brought, of course, a lot of hope, particularly in the field of education. And we keep on hearing things like how ChatGPT can be the next big thing in learning and education, how ChatGPT is at least poised to change education, and some are calling it like a plague upon education as well, right? So there are clearly a lot of varying opinions around this technology in education. But amidst all this hype, if you were to sort of look a little bit deeper into this technology, we would realize as NLP researchers that there are a lot of fundamental challenges with these models, right? These models are very expensive to train. They're very expensive to use. Very few major tech companies have the capacity to train and use these models. And if you are a university or an ed tech provider, you're really risking sort of the privacy of your students as you use these models. Then these models are really uninterpretable. It's unclear how the model is really arriving at a solution for these kinds of problems. They are not very truthful. They can give us often wrong answers. They can give us misleading explanations. Then they're also very miscalibrated. The model is often overconfident in its answers, and it's also often overconfidently incorrect, right? So if you're a student or an educator using these models, it's hard to be able to trust these models and reliably use them in educational context. Now, there are also a number of unique challenges with these models, particularly if you think about the field of education. These models are not really aligned to be pedagogical in any way, right? There is nothing as part of their training process that would let them model, say, let's say, the pedagogical nuances that you expect in one-on-one human tutoring situations, right? So over the last few years, our group has been working on some of these fairly broad set of challenges in this intersection of these two overlapping fields. And for the purpose of this talk, I'm going to focus a little bit on some of our work on thinking about how can we use these certainly very imperfect models, but also very powerful models in such a high-stakes setting like education. And in particular, how can we make these models good intelligent tutors? So let's talk a little bit about intelligent tutoring systems. So the field of intelligent tutoring systems is not new, right? There has been a lot of work in this field, and this is sort of a basic schematic of what an intelligent tutor might look like, right? So an intelligent tutoring system has a lot of components. So you have this student model right over here that is collecting essentially all the data about the student, looking at it, and it's kind of trying to build a representation of the student, a representation of the learner, and it's trying to estimate what is the current knowledge of the student. Then you have this domain model over here. The domain model maintains all the subject knowledge about what it is trying to tutor, and it's trying to use that in its pedagogy. Then you have this pedagogical model over here. So the pedagogical model takes this representation of the student that is being built over time and the domain knowledge and tries to deliver some kind of tailored instruction to the student that is personalized to this particular learner via this user interface. Okay. So all these different models come together to the kind of tutoring systems that we see today. Now, however, the sad story in the field of ITSs is that despite decades of research and development in tutoring systems, only a handful of tutors are still being used today. And one of the reasons for this challenge is that these tutors have been extremely expensive to build, right? It takes developers and system designers a lot of painstaking work in building a set of rules that capture all the kind of intelligent behavior that they are expected to have, right, in every pedagogical context. So in our research, we ask this basic, simple question, can these language models help, right? So as we just saw, these language models are good general purpose domain models. They understand, quote unquote, a lot of this kind of knowledge that is required in educational context. So it might be possible that they can help us reduce some of these tutoring design challenges that we have seen over the years. Okay, so however, there are a couple of main challenges that really stand before us before we can use these language models in intelligent tutoring. One, it's rather unclear, as I said, how do these language models interact with the pedagogical model? How do we make these language models more pedagogical? Then there is this second challenge. How do we use these language models to understand the student and generate some kind of personalized, tailored instruction to the student? So these two questions will serve a little bit as the roadmap of my talk today. In particular, I'll try to answer these questions, and then I'll try to brainstorm a little bit with you on the path forward from here. So how do we make language models more pedagogical? So in this half of this talk, I'll talk to you about two simple pedagogical schemes, and we'll look at how we can possibly integrate them into language models. So we'll talk a little bit about a particular idea called Socratic sub-questioning and a little bit about dialogue-based tutoring. So a particular instance of this kind of interaction-based tutoring that we have been working on in our lab is called Socratic sub-questioning. And Socratics is actually a very old educational method, right? It goes back to Socrates and Plato from the mythology, and it can be summarized really well in this one particular quote, right? Socrates allegedly says, I cannot teach anybody anything, and I can only make them think, right? So allegedly, Socrates would often teach Plato by asking him a set of thought-provoking questions, right? And the hope was that these questions were designed in such a way that Plato would arrive at the conclusion by himself, right? So that is the idea behind Socratics. And while there isn't a very good computational model for Socratics, in our work, we looked at a slight variant of Socratics, which we call funneling. And the idea here is to iteratively generate some set of sub-questions, some decompositions of the problem, and use it to guide students towards the solution. So let's say there is a learner, and they are faced with this particular question. Grace weighs 125 pounds. Alex weighs 2 pounds, less than 4 times what Grace weighs. What are their combined weights in pounds? Okay? So you can solve this problem in the following 2 steps. You can compute the weight of Alex, then you can add their weights, and you can compute their combined weight, right? So you can actually think of this kind of a pedagogical scheme where you could decompose the original problem into these 2 sub-questions. You can ask the student, how much does Alex weigh? And then you can ask the student, what is the combined weight of Grace and Alex in pounds? And you can hope the student will be able to answer the overall problem if they can answer these 2 sub-questions. Now, what if your student is not able to answer the first sub-question correctly? Maybe you can further decompose this problem. You can decompose it into how much does Grace weigh? And given the weight of Grace, how much does Alex weigh? And so on. So then, inspired by this idea of question decomposition as a way of instilling pedagogy, we came up with a reinforcement learning guided approach to generate these sub-questions, right? So here I describe sort of the reinforcement learning process for generating sub-questions at each level of this tree. So if you think about what are good properties of these sub-questions, right? We scoured a little bit of some of the learning science literature, and we were able to come up with these 2 possible ways of thinking about what these good sub-questions should look like. So 1, these questions should be focused. They should be directing the learner towards the content that is being learned. They should be goal-driven. So the sub-questions should be able to assist the learner in reaching the final goal, which is being able to solve the problem. So motivated by these 2 properties, we have this very simple reinforcement learning guided sub-question generation model. So the model looks like this. The model has 3 components. We have a sub-question planner, which is this thing in red. We have a sub-question generator, which is any large language model. And on the right side, I will draw out this reward module for reinforcement learning. So the sub-question planner is any large language model reasoner, like GPT-4, that you could think of. Our sub-question generator is also any language model. Then we are given this kind of a math word problem, something like this. And then we use this large language model, this planner, to derive this kind of a step-by-step solution for the problem, right, that will guide the sub-question generator in generating the questions. The sub-question generator generates these sequence of sub-questions at that particular node in the tree, and it's further guided by a reward module that computes a set of rewards. So we have rewards like fluency, which base granularity and answerability rewards. So the fluency reward essentially measures how likely is this sub-question according to a different language model. Then we have granularity-based rewards, which are measuring have we generated the right number of sub-questions? Are the number of sub-questions here the same as the number of sub-questions in the training set? And then we have an answerability rewards, which are the most important ones here. In this case, we use a smaller language model, in particular a GPT-3 model, as kind of a simulation of a student. And this reward measures whether these sub-questions are answerable by GPT-3 and whether the sub-questions can guide GPT-3 in answering the problem. Okay? So if GPT-3 has access to these sub-questions, is it better than when it did not have access to these sub-questions? These rewards then go back to the training of the sub-question generator, and the sub-question generator is fine-tuned with a simple approach such as reinforce. Okay? Feel free to ask questions, or if I should pause. Yep. So if we evaluate this approach on a variation of the GSM-8K dataset, the GSM-8K dataset has problems which require 2 to 8 reasoning steps, and they require this kind of sequence of elementary calculations. So the dataset already includes the first level of sub-questions. We further extended it to generate this kind of a hierarchy of sub-questions. Then we evaluated the quality of the sub-questions that were generated using a number of human evaluations, expert evaluations. We were able to show that the sub-questions generated by this reinforcement learning approach reduces the repetitiveness of sub-questions. So if you use just a language model, it repeats sub-questions quite a bit. So that is reduced. There is increased logical relevance to the problem, better sequencing of sub-questions. The sub-questions are usually in a more correct sequence. There is the right granularity of sub-questions, usually the number of sub-questions, and the coverage of all sub-questions is also more complete. So we have these human evaluations in the paper. Then we went on to do an actual learning experiment with learners on Mechanical Turk. So what we did here is we recruited a number of crowd workers who were asked to solve these math word problems themselves. And if a user answered a question incorrectly, we then used this sub-questioning based funneling approach as an intervention. And then we compared this kind of a treatment group, right, which had access to this mechanism of Socratic-based guidance, and we compared this group to a no questions group, which is the control group. So here is what our study looks like. The treatment group gets this kind of decomposition of questions and iteratively, whereas the control group just attempts the questions twice. So here is a plot that shows our results. So learning experiments are very complicated. So here in this particular result, we were not able to show major learning gains. There was some modest gain in problem-solving success over the entire population. We had a population of 50 learners that attempted 100 exercises in each session. But the results are interesting in a lot more nuanced ways, right? So on the x-axis of this plot, I have problems that are sorted by increasing problem difficulty. So problems on the left require less number of reasoning steps compared to the problems on the right, which are a lot more complex. Here, the control group, which did not have sub-questions, is plotted in blue, whereas the treatment group is plotted here in orange. And as you can see here, if you look at questions that are fairly simple, where the sub-questioning approach, the sub-question generation approach works better, usually the treatment group shows significant improvement. But if you look at results on the right, where the problems become a lot more complicated, there's a lot more room for the sub-question generator to make errors, actually the treatment group gets even more confused, right? This pedagogical scheme does not work, right? So this is really one of the results that is bringing out this challenge in AI in education, working with these imperfect models. You might, in some situations, see something like this, right? But you really have to be able to trust the model because it can also do some harm in certain cases. Okay, so I'm happy to take any questions before I move on. Yeah. So it cannot, right? So we also have some work in that direction. But you were able to use this smaller language model to simulate sort of a learner. And at least the idea is that it should, if it helps this smaller language model being able to solve the problem, that should reinforce the model and tell it that this is, you're going probably in the right direction. This is a reasonable sub-question to ask, right? So it cannot hurt. Yes, so I'll talk about that in the later part of my talk. Yeah. Yeah.
And with problem difficulty, what age group should be able to solve these problems?
So these are middle school problems around age group 5 to 8.
5 to 8. Okay.
Yes. But our population are all adults. Okay. So with this, I'll move on to another kind of pedagogy that we've been looking at, which is a little bit more general. And this line of work is called dialogue-based tutoring. So dialogue-based tutoring is kind of a holy grail in educational NLP. And there have been a lot of dialogue-based tutors that have been developed in various domains, right? So all through the 2000s and 2005, there are very specific dialogue-based tutors in domains such as physics, mathematics, algebra, et cetera, that have been developed. But again, in this domain, we see sort of the same problem. These tutors are very rule-based. They work on very specific domains, often very specific question types, and they require hundreds of hours of development per hour of instruction. So can we use language models to help in this particular field, right? So, but before we go there, let's just ask a very simple question, right? Can ChatGPT be used in education? Are these language models already pedagogical? So here is a very simple illustration of this challenge, right? So here I prompt some popular language models with a typical educational scenario that you might see in a classroom. So the student is given this kind of a question. James writes a 3-page letter to 2 different friends twice a week. How many pages does he write a year? This is the correct answer. It's 624. And the student confusion is that the student, in this case, forgets the word twice or does not understand the word twice. So they get to the answer 312 instead of 624. So given this situation and given this student confusion, we sample a teacher-student dialogue, a teacher-student conversation, and ask various language models what would they respond as a teacher in this particular context. So in this context, InstructGPT responds by saying, that sounds correct, great work, right? So clearly, InstructGPT is factually incorrect. The student is wrong, but it gives the student incorrect feedback. That's a problem. On the other hand, if you look at GPT 3.5, it goes on and says, you calculated the number of pages written per week correctly. However, James also writes 2 letters per week, so the correct calculation is so and so. Does that make sense, right? So in this case, what GPT 3.5 has done, it has leaked the entire solution to the student. It leaves the student with no space to reflect on their own mistakes, and this is also not a good pedagogical strategy, right? So we did this analysis a bit more rigorously, right? So ChatGPT actually ends up revealing solution to the student 66% of the time and provides incorrect to students in this particular data set 59% of the time, right? And that's a big problem. So then how do we incorporate any kind of pedagogy in language models, right? So one way is to think about how human teachers would do this in the classroom, right? So human teachers use a lot of nuanced pedagogical strategies. A teacher would, for example, elaborate upon a question. They might provide some specific kind of feedback. They might prompt a student with questions like, what is a dozen? They might provide hints or correct the student or summarize the conversation so far. There are lots of interesting pedagogical strategies that teachers deploy in these kinds of conversations. So then we started thinking about how do we incorporate this kind of rich pedagogy in language models. So one simple idea would be to go to a classroom and collect lots of one-on-one tutoring data and fine-tune these language models in this data, right? However, the problem here is that this data does not exist. In this domain, there is very little data because there are obvious privacy concerns with collecting this kind of data from students. So then, over the last couple of years, we've been coming up with a number of ways to collect approximately reasonable, pedagogically rich dialogue data in this domain. And here is one particular protocol that we have for this. So here we come up with a way to crowdsource dialogue data at scale with rich pedagogy. So the approach works in 2 stages. In the first stage, we recruit crowd workers. We have 2 crowd workers. We have real math teachers recruited on Prolific, and they are having this synchronous conversation with crowd workers who are role-playing as students, right? And we use this mechanism to collect a small amount of data. This is extremely expensive. You're actually waiting for 2 crowd workers to communicate on Prolific. They are always waiting on each other. This is extremely challenging. So then in the second stage, we actually use this small amount of data to fine-tune language models, and we replace the crowd workers who were role-playing as students entirely with these language models. So now this data set collection becomes asynchronous, and it can be scaled up a lot more better. So then we decide when to switch from stage 1 to stage 2, depending on when the teachers cannot distinguish between the crowd workers who are role-playing as students versus these language models. So this is our data collection approach. There are a couple of other important mechanics. So one of the important things is how do we simulate student confusion. So we pick the student confusion by actually sampling also from a language model. So we sample multiple solutions from language models, and we pick the most frequent incorrect solutions, and we treat them as incorrect reasoning paths, incorrect solutions from students. So there's a lot of upcoming work in cognitive science that is increasingly stating that language models, even when they are incorrect in possibly human-like ways. Now, this is still an open research question in this area. Then we have teachers who scaffold these students in problem learning through this conversational context, and they use a number of dialogue acts that I'm going to talk about next. So in order to collect this pedagogically rich dialogue tutoring data, we ask the teachers to choose from the following reasoning strategies. The teachers could scaffold the students. So scaffolding employs some of these teaching strategies like asking the student for a general purpose strategy, guiding their focus, asking them to recall certain kind of relevant information, asking for an explanation, seeking some kind of a correction, seeking word knowledge, and so on. So the teachers were encouraged to use these scaffolding acts, and they were asked to tell the student part of the solution or part of the strategy only when these scaffolding strategies continuously fail in helping them make progress. So you want the teachers to scaffold students as much as possible. So with this approach, we collected about 30,000 teacher-student dialogues on this domain of math word problems. And then we fine-tuned a number of dialogue models on this data set. So here is just a high-level overview on what this model looks like. So this is a very simple language model that is conditioned on the dialogue history so far, the problem and the student attempt, and generates the next teacher utterance conditioned on this information. So as you can see here, the model has 2 additional modules. So the first is the teacher strategy predictor that predicts the next teacher strategy that teacher should use, and this student error predictor that tracks what is the precise step in which the student makes errors. So I'm going to just brush this a little bit under the carpet, but the way we do this is by producing a solution space of different solutions from large language models, clustering them by taking the answer that occurs most frequently, using this as the space of correct solutions, and then aligning the student attempt with all these solutions to identify what is the erroneous step in the student answer. Then using this approach, we fine-tuned a number of open source language models. So these are open source language models, FLAN-T5 and OPT, and we compare it to ChatGPT. So we evaluate these tutors on 3 different metrics. The first is coherence of the answer response, of the teacher response, the correctness of the feedback that the teacher is giving, and this third aspect of what is in learning sciences called equitable tutoring, which is really measuring whether the tutors are giving students a learning opportunity. That means they should not be giving away the solution to the student. So as we can see here, each of these open source language models that are fine-tuned on our data set significantly improve on correctness of the feedback, as well as this aspect of equitable tutoring. So in conclusion, these language models fine-tuned on this data set provide more correct feedback to learners and provides them with more learning opportunities. Then based on this, we conducted this kind of a simulation study. We have the student model that we had generated during the data collection approach, where we try to interactively tutor the student model using our tutor models. Okay? So here we have three kinds of tutors. We have a very simple, naive tutor, which is basically this next step tutor that is repeatedly asking the student what is the next step. Then we have the GPT teacher, which is using ChatGPT as a teacher model, and our best fine-tuned model. So as we can see here, on the y-axis, I'm reporting the percentage of successful conversations, which is plotted here as this thing called success rate, and the telling rate, which is how many of these utterances are actually these telling utterances. So as we can see here, our dialogue tutor allows the student model to solve problems with a fairly high success rate, not too much worse from the ChatGPT model, but with a much lower revelation of the solution. Yep.
I'm a bit puzzled by the fact that you're stating that revealing a solution hinders teaching.
Hinders learning.
Solution can be informative and people can learn from seeing a solution as well. So can you tell us a bit why you're so focused here on the low revelation?
Yeah, so you're right. I think there is obviously some learning that for the student also if they look at the solution. But then the problem is it makes it hard for the students to really identify what are their misconceptions, what are the things that they have made, that they are doing wrong in terms of problem solving, right? And for them to be able to identify these kinds of general principles, it requires some kind of self-reflection on their part as the tutor is asking them sort of a more general kind, more broader kind of questions, more strategy questions, rather than just revealing every step of the solution, right? Revealing every step of the solution is no better than looking at the solution, right?
Can I ask another question? About GPT teacher, did you use some prompting engineering? Because last year we organized a shared task where some people used more prompting strategies that showed improvement of GPT over just generally using ChatGPT as a teacher.
Yes, so we were using some kind of prompts. So there was this slide where I was describing this prompt where I was showing the partial incorrect student attempt and asking it, if you're a teacher, what would you respond? Yeah.
Was it using a prompt, or is there any component in the fine-tuning model where you incorporated, saying, like, it has to, the model has to provoke the student to think of this perspective and not reading the right set of answers during the conversation? So that happened in the prompt part or in the fine-tuning itself?
So in the fine-tuning part, yes, our open source language models were fine-tuned on our data set, which had much lesser amount of telling, right? Much lesser amount of revealing. For the ChatGPT model, I'm not 100% sure exactly whether this was also part of the prompt, but I can check and tell you after my talk from our paper. Thank you, that was a good question. Okay, any more questions on this part? Okay, great. So then I'll move a little bit to the second part of my talk, where I want to talk about how can we make these language models, how can we help them generate personalized instructions for each learner. So the inspiration for personalized instruction and personalized learning comes from the fact that good instruction should actually be customized to the student. It should account for their prior knowledge, their current knowledge, and it should also account for their individual learning styles and their differential learning capabilities. So here is a plot taken from some of the learning science literature, where the learning science literature talks about what is called the Vygotsky zone of proximal development. So here, this is like plotting out the set of zones of what can or cannot help a student. So here is like a too easy zone. So this is what the student can do without help. This is the too hard zone. This is beyond the student's individual abilities. And this zone in the middle is really what the student can actually do with some assistance. So the theory of proximal development says that optimal instruction should really lie here, right? So we should understand the current knowledge state of the learner, and we should challenge them just a little bit so that they can learn. So a particular example that you've already probably seen for this kind of personalized learning in language learning context is Duolingo. So in Duolingo, they continuously build basically your estimate of your learner skills. So it builds this kind of plots which tells us what is the learner's skill at this point of time. And then it uses this estimate of the learner skills to provide them some kind of recommendations on what are the next set of things that they could do, the next set of tasks that they can do. So for example, here the learner is being recommended that they go and practice gerund verbs, and in particular these weak words. And this continuous estimation of the learner's skills are then used to provide them with exercises. So for example, on Duolingo, you've seen these adaptive translation exercises where the learners are provided these exercises like this, right? So here the learner is trying to learn English, and they're provided this translation exercise in English, and their job is to translate this exercise word by word into another language that they already know, right? So one of the challenges in Duolingo is that Duolingo is constrained to recommending learners exercises essentially from a fixed pool of exercises, right? And this is a very laborious process. So we started thinking about whether language models can be used to generate personalized instruction for each learner, personalized exercises for each learner on the fly. So in order to tackle this problem, we proposed a solution where we combine a time series model in education called knowledge tracing with a controlled text generation approach. So here is a high-level problem framing that we are going for. So we are given a learner's history that I denote as h less than n. So the learner's history is essentially a sequence of exercises, E1 to En, that the learner has attempted so far. Each exercise is essentially a sequence of words. And for each exercise, I have also the learner's response, which I denote as these per word correctness labels, this vector where at each position, I know whether the learner was able to translate that word correctly or not. Okay? So I have this historical data about each learner. And my goal is to generate the next exercise for a learner, which is En plus 1, based on the learner's current knowledge state, which I denote as Sn plus 1. So this is basically an estimation of this dynamically time-varying knowledge of the learner and a set of system constraints. So I represent this knowledge state, Sn plus 1, essentially as this vocabulary dimensional vector. So this is a v-dimensional vector where at each position in this vector, I will have the student's mastery of the ith word, right? So this tells me what is the probability that the student will be able to translate this particular word correctly if they see it, okay? So this is just a representation of the student's knowledge space. So the generation of this next exercise, En plus 1, is based on the student's knowledge state, as well as a set of systems constraints, right? So here are a set of constraints. So for example, you might want to have a constraint like this, where you say that certain knowledge components should be in this exercise, right? So in Duolingo, it often happens that if the student is in the exercise is in the adjective part of their curriculum, you want to incorporate that kind of constraint. You want to generate this next exercise that also has a preposition, right? So we treat, in this case, individual words as these knowledge components. These are a set of words, set of constraints that these words should be in this exercise. The other constraint is about the expected difficulty of this new exercise. So the expected difficulty of this new exercise is defined here as the expected number of errors that the learner will make on this new problem. Okay? So Sn plus 1 here is the probability of the student correctly translating this particular word. So the right-hand side is the expected number of errors that the student will make. Okay? Okay, so based on this definition, here is my overall model. So I have this learner history of the entire learner, h less than n. Based on this, I will learn this knowledge tracing model, this time series model, that will build a time-varying estimate of the learner's knowledge state. This is this vocabulary dimensional vector that I was talking about. Then we have an exercise generator that will be conditioned on the knowledge state of the learner and a set of constraints, the difficulty of the new exercise, and maybe a set of words that I expect to see in the next exercise. And it will generate the next exercise, En plus 1, for this particular student. Okay? So here's the overall model schematic. So let's look at all the different parts of this model. So the first module here is this knowledge tracing model, this knowledge tracer. And it looks like this. So let's say a student's historical data comprises here of a set of exercises, a cat, a round ball, an ant. And for each of these exercises, I also have these correctness labels, which correspond to whether the student translated that particular word correctly or not. Then we embed each of these tokens in the exercise, as well as each of these correctness labels. We pass each of these representations into any kind of a black box encoder, typically an RNN or a transformer. This gives us, this basically maps all of this historical student data into a set of hidden states, where each hidden state can be thought of as summarizing the student's historical data up until that point. Then these hidden states are projected using a sigmoid layer to these set of knowledge state vectors, these vocabulary dimensional vectors that I was talking about. And then these estimated knowledge states are then used to predict the correctness labels for the student for the next exercise that they are going to attempt. Okay? So this entire model is learned by minimizing the cross-entropy loss between the correctness label for, let's say, the jth word in the ith exercise and the correctness probability according to the knowledge state predicted after the previous exercise. Okay? So then this is also a time series model, so we should also say that this knowledge state of the student should not change too much between consecutive exercise attempts. So we also penalize the 2 norm between the difference in their knowledge state between 2 consecutive attempts. Then we have this controllable exercise generation model, which is basically any autoregressive language model. So just to summarize, we have a language model which typically generates the next token WT given a history of tokens. In this case, we also condition the language model on an encoding of the student's knowledge state, an encoding of the required difficulty, and an encoding of the required set of words. Then, in order to learn these 2 models, the knowledge tracing model and the exercise generator together, we have this additional loss term, which basically says that the difficulty of the exercise as per the knowledge state should be as close to the desired difficulty or not as well. Okay. So one of the challenges in this model is now decoding from this language model. I have these difficulty constraints, and I want to satisfy the fact that the difficulty of the exercise that I decode should actually be this desired difficulty, right? So here is how you would think about decoding from a language model. In a typical language model, you could do greedy search, where you could sequentially keep on taking the highest scoring next token to reconstruct the output. A slight improvement, of course, most of you know about this, is beam search, where you, instead of taking just the highest scoring one particular node, you retain some set of k nodes. So here is a possible update rule for beam search. You take the beam at time step t minus 1, yt minus 1, explore all possible generations from there on, and prune the beam back to size k. Okay, so but now here we have constraints, right? So in this case, one way to incorporate these constraints is to think about including these distance to constraint satisfaction in your objective. So you have these indicator constraints that there are certain words that must appear in the output. And then you have this particular constraint FD, which is quite tricky, that the difficulty of the sentence D hat should be as close to D as possible. Now the problem here is that this does not work. And the reason why this does not work is that if you are kind of myopically applying these Fs, right, to rescore these beam, it really biases the decoder to have difficult words initially, right? So if you're looking at language learning in English, you're generating very difficult verbs. Verbs typically appear in the second position, and this is a problem, right? So a fix that we came up with here is to have a very simple look ahead. So if you are scoring a subsequence during beam search, we also look ahead. We have a look ahead of L steps, and we sort of estimate this future estimate of F and incorporate that in our scoring mechanism. Okay, so lots of description of this model. Now I move to the experiments. So we evaluated this model on 1 million interactions of 2,600 learners. Over the first 30 days, they were learning a second language, in this case, English on Duolingo. So here in this table, I report various quality measures for exercise generation. So I have automatic text generation metrics like blur and meteor. I have coverage of known knowledge components, which is basically how many of the words that I expected to see are actually covered in this exercise, as well as this notion of difficulty control, which is whether the difficulty of the exercise was the same as the expected difficulty. So here we see that our adaptive and personalized exercise generation model outperforms a number of non-adaptive and non-personalized approaches on each of these criteria. And then in order to showcase some kind of an educational utility of this model, we do some kind of simulations, right? So what we did here was we randomly sampled 50 students from our data set, and we created a curriculum of 30 exercises for them. And in order to create these exercises, I have two methods. So I have this method that we call Expectimax Gen. So this method is generating exercises using our method, exercises that lead to the best expected knowledge gain. And I have this retrieval-based method, which is basically selecting exercises that lead to the best knowledge gain. This is what Duolingo currently does, right? And on the y-axis, we are plotting the average predicted knowledge state. So what we can conclude from this is that if we are adaptively generating exercises, this can lead to better learning efficiency compared to just selecting the best exercises from a fixed pool. Okay, I'm happy to pause for a minute. Okay, so in the next minute, I just want to give you a little bit of an overview of a few other things that our group has been working on. So we've been working on also these foundational language models. In particular, we have some work on causality that quantifies sort of the robustness of how these models are robustly solving these kinds of reasoning problems. In particular, here we think about the difference between the ground truth reasoning mechanism. So if you are solving a problem, an addition problem, this is sort of the ground truth reasoning mechanism, and other ways in which spurious correlations can come in terms of these models. And these spurious correlations, we can quantify them by looking at their corresponding causal effects, and that tells us a little bit about reasoning. Then we've done some work on sort of compute efficiency of these language models. Can we distill these large models into much smaller models by looking at explanations? In particular, here we see that if we have a sub-questioner and an answerer instead of one language model, then this distillation works much more efficiently. We have a lot of interest in mechanistic interpretability, where we think about how is this model reasoning about these problems. If it's asked what is 15 times 20, what is the mechanism that it takes to generate this answer? We have also some interest in verification and estimating uncertainty, and also data efficiency is another interesting aspect. So if you are a human, you can look at this one particular problem and solve it, but if a language model encounters this problem, it's almost guaranteed to fail. And then on the other end, we have some work on tutors where this work sort of dovetails, and we are currently thinking about how can we incorporate model confidences and these kinds of correctness estimates to build tutors that can work in these kind of high stakes domains. Okay, so with that, I'll end. Thanks a lot, and I'm happy to take questions. Are you referring to completeness of the solution?
Yeah.
Okay. I'm not sure if I understand your question exactly, but one of the challenges here is verification. We have to verify whether the student at the end is able to solve the problem correctly. That's a fundamental part of the challenge, right? And in order to do that, there are, in some domains which are more closed-ended, there are simple ways to think about this, but in more open-ended domains, that is quite challenging, right? And that might require maybe some kind of tool augmentation, some specialized modules. So there's a lot to do in this area.
But then you got together with some verification tools to do that, or?
Yeah, so verification is its own beast, right? And I think there's a lot of scope in looking at these language models also for verification and sort of integrating them with these tools like Rust is one of them that programming languages people have been building for quite a while. So yeah, there are lots of challenges though. To human tutors? That's an interesting question. So currently we're trying to run some of these studies in the classroom where we mostly are trying to still think about whether these models can work in real situations. You're running these RCTs. Comparing them to one-on-one tutoring by humans, I think that is interesting. That would be one of the things also that we should look at. But so far, we don't have even pedagogical validity of our model.
When you looked at the success rate and like the telling rate, you wanted the high success rate but a low telling rate. Was the success rate success when given the instruction, and then sometimes the success is very high because you just gave the right answer? Or did you also measure like success rate on sort of for the students, like a held out test set where they don't get access to the tutor, because maybe that's the end goal then to
Yeah.
without.
Yeah, so that's a very good question. So it sort of points to this this difference between short-term problem-solving success versus long-term learning, right? And that's difficult to quantify. So one of the things we were looking at in the control experiment that I was talking about earlier was also sort of this long-term learning effect, but we were not able to successfully do it and show any significant learning gains there.
Okay, is there another question? We maybe have 2 more minutes. If not, let's thank our speaker again.